will introduce my co-authors. The first author is Yi-Jiun Huang, and me, and Shinn-Yan from TL Taiwan, and also Dr. Yang from KRISS, South Korea, and also Dr. Fujieda from NICT, Japan. And online, I will introduce the software-defined receiver, the motivation, and some details. And the second is experimental setup and the results. Finally, the conclusions. And when we talk about the instability of a two-way link, we will always talk about the path instability. And that goes to the path delay difference, also the Tseng-Yang effect, and the ionosphere delay, and the troposphere delay, and some instability in the station delay, and some factors like environmental factors and also the satellite movement will affect the path instability. And we use the two-way method to cancel out most of the delay. But however, it is difficult to address the unpaired variations, such as side-dependent variations that it cannot cancel out. And now, more and more research will talk about the measurement noise, because in the two-way satellite and fusion, we use the different codes and the slightly different frequencies. And here is the signal transmitted by the searching modem. So it's a 2.5 megachip PRN code. The TS code is like this. When the signal passes through the bandpass filter, we use the SAW filter in our system, and some equipment, the signal becomes like this, and we transmit to the station to the satellite and receive back. The signal is like this, and finally the receiver receives the signal like this. So when the transmit signal and receive signal is not the same. And the largest unstable source is probably due to the received signal. They may be shaped by the product of the bandpass effect by the transmitted and received equipment. So the measurement noise is very important, and we need to improve the receivers to overcome some measurement noise. And this is the car I have driven. And as you know, the next car will be much safer, because they called it as the driverless self-driving car, using the intelligence algorithm and some sensor, also the GPS. So the future car will like this. And how about the two-way modems? Here is the modem I have performed. This is the modem, Atlantis modem, and also the NICT multi-channel modem, and now is the station modem. And what is the next? And we'll be talking about the software-defined radio technologies. We have performed the DPN two-way using the AWG and analog to digital sampler. And Fujieda Sung has also introduced the two-way carrier phase. And here we will talk about the software-defined receiver here. And here is the configuration of the time transfer using the software-based technology. The signal is 70 megahertz in our system, and the 2 SLO analog to digital sampler. And here is the software system here. And we use the cross correlation system and to perform the carrier tracking control and also the call tracking loops. So this is a software receiver. And now we remove the delay lag loop like this, and the code is the open loop system in our new system. And what is called the open loop software-defined receiver? And we use the multiple correlators instead of the delay lag loop here. And so here is the PRN signal, and we use the multiple correlator using the multiple different delays to calculate its correlator output. And the delay measurement will be determined by the position of correlation peak. When the signal power changes, the delay measurement will keep the same. And here is the implementer of the SDR. We can use the optimal parameters and the algorithm to determine the signal arrive time. That's TOA. And so now we using the open loop configuration to develop our software function. And some function like here is high resolution correlator, and also the successive interference canceling now is under test. And the new algorithm may be using a multi-channel reception. And so this is the SDR. And then we'll introduce the experimental setup. Here is the conventional two-way system. The station modem is used here. And when we add the pulse splitter in the reception port, we can divide the signal to and connect to the SDR. SDR is consists of the amplifier to adjust the power level, and also the analog to digital converter, and finally the computer. And so the system can be performed simultaneously. It's a parallel measurement between the conventional two-way system and the software-defined receiver. And here is the setup. It's quite simple. We just need to connect the device and adjust the input signal level and start operations. And here's the computer, and here's the A to D sampler. And here is the picture for the connection, and the 10 megahertz signal, 1 PBS signal here. And here is adjust the input signal level. We adjust the signal level to the optimal range. So this signal is too weak, and it is a saturated situation. We need to keep the signal like the bell shape, like this or this. And finally, just start the operations. And the measurement will be stored in the probe. And then I will introduce the experiments that we have performed in the Asia-Pacific two-way networks by the satellite Eutelsat 172A. And the 3 laboratories have performed the SDR and the two-way system. It's TL in Taiwan, NICT, Japan, and KRISS in Korea. And here shows the experiment results. And the first one, we will compare the two-way hourly data. The blue curve is the SDR, and the two-way performed by the C3 is in the red curve. You can find some diurnal here, about 0.5 nanoseconds. And here shows the time deviation here. You can find the C3 related here. At the 1 hour, the T depth is about 122 picoseconds. The SDR have a better short-term stability, and there's no diurnal here. And when the averaging time larger than 2 days, the result will be consistent. And here it shows the results for the NICT TL links. You can find similar results. In the results of C3, they have diurnals larger than 0.5 nanoseconds. And in the T depth, you can find the SDR have a better short-term stability. And there is no obviously diurnal peak. And here is for the KRISS NICT link, similar results. No strong diurnal in SDR, but they still have in C3 results. Then I will show the experimental results compared with the GPS PPP. And this curve is GPS PPP as the two-way SDR results. And here shows the PPP minus the two-way C3 results. You can find the diurnal is obviously here, but the unobviously for the SDR results. And here shows the modified Allen deviation for the double difference between the PPP and the SDR. They have a better stability here. And for the conventional C3 results, not so consistent with the GPS PPP. And here shows the time deviation here. This is a GPS PPP results, and this is a two-way SDR results. GPS PPP results have a better short-term stability because they use the carrier phase data. But for the data larger than 1 day averaging time, the SDR have shows a good result here. And finally, I will show the experiment results. It's called the ranging data. It's from TL to KRISS, received by the KRISS. So it's the ranging data. And they have two ranging data obtained by the C3, and the SDR is the time interval data here. They're almost the same because it's the scale is very larger. And here is the differential between the two results, the C3 and the SDR, half of them. And you can find that the signal from TL and received by KRISS, they have a diurnal here. But from the NICT to KRISS or KRISS to KRISS, received by itself, there's no obviously diurnal here. So we maybe find the TL C3 data maybe have some we call the site-dependent variations. So here is another result show the data obtained by the TL. So the signal is transmitted by an NICT and then received by the TL station. And here is transmitted by the KRISS and received by TL stations. And we can find that both of them have the diurnal here. So we just, I just want to tell you that the data of the C3 is more sensitive to site-dependent diurnal variations. But the SDR, we have reduced this effect. And I will tell you some reasons, maybe can explain that. The TL station have some asymmetry spectrum. Since we use the SAW filter to cut off the frequency. However, our converter, the step is we can use the step is just 1 megahertz. So several spectrum will be cut off like this. So here maybe a reason cause the side-dependent diurnal in here. And finally, I will show you the crucial sum results. And the blue curve is the results, crucial results obtained by the SDR. And ideally, the crucial sum results will be very close to 0. And the SDR results here shows they have a very small standard deviation and much closer to the 0. And here is the set tree data. They are much far from the 0 and have a larger standard deviation here. And finally, the conclusions. We have introduced a software-defined receiver here and demonstrate the data of SDR. They show a better precision and less diurnals. The diurnals may be side-dependent, and the SDR is a useful tool to survey the noise of the two extensions. And for further verify whether the function of SDR is reliable, more experiments and collaborations between the laboratories are required. And finally, thank you for your attention.